Well, good evening, ladies and gentlemen. This is once again your well-rounded math teacher, Mr. Pekar. And today we're working on Unit 2, Video 5 for our notes. Learning targets. I can graph two variable inequalities. And more importantly, I can graph absolute value equations and inequalities. Okay, so we're going to start out with simply graphing inequalities. And a couple things we got to know. When we're working with inequalities, we're working with less than and greater than symbols. And when we graph the line is not actually the answer in this case, or where our solutions are. It's called a boundary. And it requires a dotted line or a dashed line. In less than or equal to or greater than or equal, it's a boundary. The line is also a solution. So in this case, we'd have a solid line. And that's about it for that. So we're going to graph one here. And the first one we're going to graph here is 2x plus 3y is greater than 6. Okay, this is in standard form. X and y are on the left-hand side, and my constant, just my number, is on the right-hand side. First, you've got to graph the boundary, which is 2x plus 3y is less than, greater than. Actually, we're going to say this, equal to 6. Okay? It says to find the x-intercept, y-intercept, and slope. I think the easiest way to do this is to put it in slope-intercept form and then graph it. But if we're going to find the x-intercept here, the easiest way to find the x-intercept is, and it's where it crosses this x-axis right here, and that's when y is equal to 0. So if they ask you to find the x-intercept, just plug in 0 for y. 2x plus 3 times 0 equals 6, or 2x, this is just going to equal 0, so it cancels out, equals 6, and you can see that x equals 3. So my x-intercept is 3. Now to find the y-intercept and the slope, well, and that's how we're going to graph it also, I think, is just put it in slope-intercept form. In other words, solve your equation for y. I think that's the easiest way to graph lines, or in this case, when we're working with inequalities, boundaries. Now, I just said this equal to 6 right here, because we're going to graph the boundary. We'll come back to the greater than in a second here. But anyway, solving for y. I'm going to subtract 2x from both sides because we have to get y by itself. This is positive, so it's positive 3y equals. Put your x term first, negative 2x plus 6, and this will eventually be in slope-intercept form. Now let's divide everything by 3. In other words, both terms, or the other side, by 3. I get 1y, so now it is solved for y. Negative 2x over 3 is just negative 2/3 x, and then 6 divided by 3 is plus 2. There it is in slope-intercept form, which is, move this down a little bit here, which is, y equals mx plus b. M is your slope, and you can see that's negative 2/3. B is your y-intercept. Your constant here is 2. That's your b. So my y-intercept is 2. So graphing this, I'm going to graph the y-intercept first. There it is. Y equals 2. Slope is negative 2/3. So using rise over run, I'm going down a negative 2, but it's a positive 3. A lot of people, for a negative slope, they'd go down 1, 2, and then back 1, 2, 3. They'd make both of them negative, and that's wrong. So down 2 over 1, 2, 3. There it is. And you can do it again. Down 2 over 1, 2, 3. Or you can go backwards, up a positive 2, but back a negative 3. And this is the original line that we're graphing, or inequality. We just put it in slope-intercept form is all. But you can see that it's a greater than symbol, so it is a dotted boundary. And here's the deal. All our solutions are going to be in one of these half planes. You have half plane 1 up here, everything above my line, and then half plane number 2 down below the line. One of those two half planes contains all the solutions for this inequality. So how do we find that? Well, we'll use a checkpoint usually. And I say our checkpoint, if your line or your graph doesn't go through the origin, that's the easiest one to use. So we'll call it a test point. We're going to test the point 0, 0. We're going to plug it into the original inequality. 2 times 0 plus 3 times 0 is greater than 6. Well, 0 times anything is 0. 0 plus 0 is 0. Is 0 greater than 6? This is false. So that means 0, 0 is not a solution. That means all these points, wherever they lie on the below the line, are not solutions. So we shade above the line because all these points, if I pick this ordered pair right here, 1, 2, 3, 4, 4, 2, if I plug that into this inequality, it should be a true statement. And there we go, graphing inequalities. Here's another one. You should probably hit pause and try it yourself, and then I'll show you the way I would do it. Okay. They want us to find the x-intercept, y-intercept, and the slope. The easiest way to find x-intercept is plug in 0 for y. So negative x plus 2 times 0, I'm going to say equals 4. For right now, when we graph this and start shading it, we'll worry about the inequality. So negative x equals 4, or dividing both sides by negative 1, I get x equals negative 4. So my x-intercept is negative 4. If they want you to find it, that's how I would do that. Okay. Now, negative x plus 2y equals 4. Let's graph the boundary for this inequality. Solving for y, to put it in slope-intercept form, I'm going to add x to both sides. These cancel out. 2y equals x plus 4. Now I need just y, not 2y. So I'm going to divide both sides by the deuce. That's German for 2, no big deal. Y equals, this is a 1 in front of that x, 1/2 x plus 2. So, y-intercept, you can see, is 2. Slope is positive 1/2 this time. So, 2, and then up 1 over 2. Up 1 over 2. And you can keep running the slope as much as you want. I'm also going to go down 2, a negative 1, and back a negative 2. Negative divided by a negative is a positive. That would give me the 1/2 here. So down 1, back 2. Now, once again, it's just greater than, not greater than or equal to. So my boundary is a dotted line. We got half plane 1 up here, and this region is half plane 2. One of these two regions contains all the solutions for our original inequality. I would use, for a test point, I'd use 0, 0 again. Okay, so plugging that in, negative 0 plus 2 times the 0 is greater than 4. Well, this is 0 is greater than 4. 0 is not greater than 4. This is false. So, not a solution. Once again, shade above. If it would have been true, then I would shade below because it is a solution. Manny has $15 to spend at the fair. It costs $5 for admission and 75 cents for each ride ticket and 25 cents for each game ticket. Write an inequality for the number of ride and game tickets he can buy. Okay. 75 cents for each ride ticket, so I'd say 0.75 times R for the number of rides plus 0.25 times G for the number of game tickets he's going to buy. It also costs $5 to get in. Now, he has $15 to spend. He can spend no more than $15. So this has to be less than or equal to 15. Now to clean this up a little bit, I'm going to subtract 5 from both sides and just say 0.75r plus 0.25g is less than or equal to 10. So basically, if you take off the admission costs, you have that much money left, $10 left. If he buys 10 game tickets, how many ride tickets will he be able to buy? 10 game tickets. So that's 0.75r plus 0.25 times 10 is less than or equal to 10. So 0.75r. 10 times 0.25 is 2.5. Just move your decimal place one place. Less than or equal to 10. Solving this for r to see how many ride tickets we can buy, I'd subtract 2.5. And 0.75r equals 7.5. Finally, dividing both sides by 0.75. Most of you can do this in your head. If you can't do it in your head, you're going to use your handy-dandy calculator here. If I can get mine to come up. Maybe I can't. Well, it's 10. 0.75 goes into 7.5 10 times. So ride tickets we can get are 10. I'll let you try these next two on your own. Okay. Absolute value function, shifts, things like that. We've graphed absolute value functions. I told you guys to make a table. When we graph absolute value, it's going to be a V. It's either going to be a V that's a shape of a V opening up, or if there's a negative in front of your absolute value here, it changes everything to open down. Now, it talks about being able to find the vertex. It's not the easiest thing. This particular function, because there's no negative times the absolute value, there's no negative in front of it, is going to open up. So your vertex is going to be a minimum point. This absolute value controls your lowest point, basically. The lowest value you're ever going to get here is when you plug in -5 for x, because -5 plus this 5 would be 0. 0 is the lowest that this can be. If I put -6 in there, it's -6 plus 5. That'd be -1. When I take the absolute value of it, it is 1, so you'd be adding that 1 to 7. So you can find the vertex. Take everything inside there, x plus 5, and just set it equal to 0, because 0 is the lowest that this absolute value is ever going to allow your vertex to get. So I subtract 5 from both sides here, and I get x equals -5. This is the x value of my vertex. So vertex, -5. Now once again, if you don't understand this, you can just use a table if you want, plug in -2 to 2 and see if you can find your vertex that way. We need the y value of our vertex. It's very simple. It's just this 7 on the outside. Because if I plug the -5 back in up here, the absolute value of -5 plus 5 plus the 7 on the outside, well, this is going to give me 0. So 0 plus 7, y would then equal 7. So -5, 7. One way to look at it is, what would you plug in for x to make everything inside the absolute value equal to 0? In this case, it's -5. And then just take this constant on the outside for your y. And that's how you find your vertex. And we'll look at that a little bit. It's nice to be able to find your vertex first, because then you can kind of graph your absolute value problem a little bit easier. So this first one, number 4, we're just going to graph this absolute value. A lot of times I just set up a table, x and y, and I'd plug in -2, -1, 0, 1, and 2. Because I recognize its absolute value, I'm going to graph some kind of a V here. I just need to find the vertex. Well, x plus 1, the lowest it's ever going to be for a value is 0. Well, what's going to give it a value of 0? Solving this, I get -1. So for my vertex, I know this, x is -1. What's my y value? -2. Because if you plug -1 in here, you get -1 plus 1 minus the 2 on the outside. This is going to give me 0. I'm just left with f of x or y equals this -2 right here. So we found this, -1, -2. That's basically our vertex right there. And just to see how it opens up, I'll graph that. -1, -1, 2 right there. That's the lowest point of my vertex. If we plug in -2 for x up here now, remembering that y is the same thing as f of x, -2 plus 1 minus 2. So that's the absolute value of -1 minus 2. Absolute value of -1 is 1. 1 minus 2 is -1. So -2, -1. So it should open up something like this. When we plug in 0 up there, I get the absolute value of +1. 1 minus 2 is still -1. 0, -1 is right here. And you can see that's enough to graph it. You found the bottom point. You could also plug in 1 and 2 to make sure it opens up correctly like that. If I plug in 1 plus 1, that's going to give me the absolute value of 2 minus 2. This is 2 minus 2, or 0. 1, 0 is this point right here. And when you plug in 2, you're going to get 1, and that's this point right here. Now, this was an absolute value function because it was an equal sign, so I don't have to shade anything here. The next one, it's also equal sign, but we're going to change that. We're going to change that to a less than symbol. So this is what we're actually going to graph. Y is less than the absolute value of x minus 4 plus 1. Okay, so we can get into some shading here. Now when we graph this V, it's going to be dotted. It's going to be over here on this graph somewhere. And we're going to have two regions. I'm going to have region 1 inside of it and region 2 on the outside of it. I'm going to pick a test point, plug it into the original function here, or inequality, and see if it's true or false, and then shade one of those regions. So it's very similar to a linear equation. If you don't like finding the vertex, you certainly could do this. X and Y, -2, -1, 0, 1, and 2, and see if you could find your vertex this way. However, when I do this, my lowest point for this absolute value for this function here is going to be when this is its lowest actual value, and that's going to be 0. X minus 4 equals 0. Adding 4 to both sides, I get x equals 4. So I know this. I'm going to have to go down a little bit lower, 3 and 4, just to get to the vertex, and I'd plug in 5 just to see how it goes up on the other side. Anyway, when I get 4, plug 4 in up here, I'm just going to say this, y equals right now, because we're just graphing the boundary, 4 minus 4 plus 1. That's 0 plus 1, or just 1. So 4, 1, right here is my vertex. Sometimes they're easy to find, sometimes it's a little bit more technical. 4, 1, that's the lowest that this graph is ever going to go. Okay, so let's plug in 3, see what we get, and go from there. Absolute value of 3 minus 4 plus 1. That's the absolute value of -1 plus 1. Absolute value of -1 is 1 plus 1, and that's 2. So 3, whoops. When I plug in 3 for x, I get 2. So over 3 and up 2. Now let's plug in 5. Make sure we're going up on the other side here. Absolute value of 5 for the x now, minus 4, plus 1. Absolute value 1 plus 1. Well, it's 1 plus 1, and once again, that's just 2. Usually when you go one to the left of your vertex and one to the right of it with your x's, you should get the same value. And there it is. Now, here's the deal. We're just graphing a boundary right now. You could graph a few more points. You could plug in 2 and 1 and 0. You're going to see this, that my boundary, and it's going to be dotted because it's just greater than, is going to look just like this. I got region 1 here and all of region 2 below it. Which one of these are going to be all my solutions for this absolute value inequality? Well, let's use a checkpoint or a test point. I'm going to test 0, 0 because I can. 0, 0 is not on the graph itself here, so that's the only point you couldn't use. Okay, I could use a point inside of it right here. I could use 1, 2, 3, 4, 1, 2, 3. I could use this point right here, 4, 3, as a test point. It's just easier to use 0, 0. So plugging in 0, 0 into the original inequality. Remember, we didn't want this one. 0 for the y is greater than absolute value of 0 minus 4 plus 1. Well, this is 0 is greater than the absolute value of negative 4 plus 1. Absolute value of negative 4 is 4. 4 plus 1 is 5. So basically we're saying is 0 greater than 5. Once again, we get a false test. So that means this is not a solution. So I would shade inside. All these points inside this absolute value are a solution. Last one, this kind of screws people up because there's a number outside of that x. Now, here's the deal. That 2 is positive, so what that means is I'm going to multiply 2 times, whenever I take the absolute value of a number, it's positive. I'm going to get a positive number when I multiply 2 times that absolute value, whatever comes out of it. So this is going to open up. If this was negative 2 here, negative 2 times anything that comes out of there is going to be negative. So that would open down. That's how you can tell if an absolute value function opens up or down. Anyway, finding the vertex, once again, you don't have to find the vertex. You can just do negative 1, 2, or negative 2, negative 1, 0, 1, and 2 if you wanted to. But I'm going to find the vertex. The lowest point is when the absolute value, whatever you're taking the absolute value of, is equal to 0. Well, there's only x in there. Well, that's when x is equal to 0. Simple enough. So this, when I plug in 0 for x, that's going to be my vertex. Okay? So if I plug in 0 for x up here, I get y equals, I'll worry about the inequality when we shade it, 2 times 0, absolute value of 0, minus 3. Well, absolute value of 0 is 0. 0 times 2 is 0. 0 minus 3 is negative 3. So there's the lowest point of this vertex. 0, negative 1, 2, 3, and it opens up. And a lot of people would just go up 1 over 1 and go like this. Well, this one's a little bit different because you're multiplying something times that absolute value. It's kind of like a slope a little bit. Let's plug in negative 1 and see how it opens up going to the left of my vertex. Y equals 2 times the absolute value, negative 1 minus 3. That's 2 times 1. Absolute value negative 1 is 1. So that's 2 minus 3, or negative 1 right here. So negative 1, negative 1 right here. Once again, it's not greater than or equal to, so it's just a dotted line going up like this. If you plug in 1, you're probably going to get the same thing. Absolute value of positive 1 is 1. 1 times 2 is 2. 2 minus 3 is negative 1. So 1, negative 1 right here. There it is. There's my absolute value function. I just need to shade it. I got this region 1 on the inside of it. Region 2 is everything on the outside of it. Can I use 0, 0 as my checkpoint? Well, it's not on the graph of the boundary at all. It's right here inside. So now my test point is inside my vertex. So I'm going to test 0, 0 again. What do we got? 0 is greater than 2 times the absolute value of 0 minus 3. So 0 is greater than, well, the absolute value of 0 is 0. 0 times 2 is 0. And I end up with, is 0 greater than negative 3? Finally, we have a true statement. So that means I shade the side that contains that checkpoint. Well, that means I'm going to shade everything inside here. There we go. There we go. Graphing absolute value functions. And we are done. Enjoy your worksheet. And peace out, Girl Scout.